Hi and welcome back. In the last episode I talked about the central limit theorem, and if you haven't watched that you should definitely go back and see that before proceeding, and if it's not very clear maybe watch it again. We closed with this message talking about that theorem. We're confident that we can answer questions about sample means now in the same way that we could answer questions about individual scores. Remember, with the individual scores we had to rely on the fact that the variable that we were studying was already normally distributed in the population. And we learned last time, thanks to the central limit theorem, we can presume that the underlying background sampling distribution that we're going to reference would be or will be normally distributed. All right, the central limit theorem says that a sampling distribution will approach normal if the sample size that we're using is sufficiently big, and that it gets even more normal the bigger the sample size we use. All right, so see all that in the central limit theorem video if that still is a little fuzzy to you, and check out your textbook and read about it there. Okay, so since we're dealing with normal curve here, we can standardize the sample means almost precisely the same way that we did with the z-scores for individuals. So let's take a look at what I mean by that. We're going to be converting the sample means to z-scores in a way that it's identical, just about identical, just a couple little extra little twists that you'll see in a second that we have to do, extra steps that we have to take. But the steps, the formulas, and then the resulting the formulas you see in a second are going to be just about the same. They look very similar. And of course the z-score table that we'll use remains the same. We'll use that same z-score table found in the back of your book. All right, now up till now we've been using what I'm now going to call the original recipe. All right, I'm old enough to remember when KFC used to be called Kentucky Fried Chicken. I bet some of you didn't even know, didn't even question, didn't even wonder what KFC stood for. Okay, it's been KFC for a lot of years now. Years ago they decided that I guess maybe the word fried had a bad connotation. Or maybe they thought Kentucky had a bad connotation. I don't know. They didn't want to go by Kentucky Fried Chicken, so they just changed their moniker to KFC. I'm also old enough to remember all the way back when you went to Kentucky Fried Chicken, you could get chicken, all right? And it was fried chicken. And then I remember when they came out with something called the extra crispy recipe, all right? That's been there forever too now, so I'm old as dirt, so I can remember when there was only one formula, one recipe. Anyway, they went on to call it the original recipe and the extra crispy recipe. So this is our original recipe for doing z-scores in what I call forward problems. All right, so when we know the score, we plug it into this little simple formula here, and we have to know the population mean and the population standard deviation. If we know those three things, we can jerk that score into its resulting z-score. And then we can look up in the table and answer questions about percentage. What percent is at or below? Or we could take any two scores and say, what percent of the population is between these 2 points, these two scores, these two z-scores? Anyway, endless things that we can do with this handy-dandy original recipe formula and our z-score table. Okay, well, your book isn't going to call it these crazy names, so don't expect to find it there, but now that we've turned our attention to sampling means, and we're going to be dealing with a sample mean, an x bar now, instead of just an individual raw score x, okay? So we have to modify this z-score formula ever so slightly, okay? So instead of using just regular x, now we're using x bar, hence my term x bar, extra crispy recipe, all right? And instead of using just the standard deviation from the population, we now will be using, in reference to x bar, we'll be using the standard, the mean of the means, okay? Did I call this a standard deviation a moment ago? Sorry, I apologize. This is mu. This is the population mean. I got a little ahead of myself. Let me say that all over again. Instead of referencing the population mean like we did over here in the original form, we now are going to be referencing the mean of means. Now, don't panic and wonder, oh my God, where do I get the mean of means from? If you know the population mean, and for these problems, we're still assuming we know the population mean, then you know what the mean of means will be, because the mean of means is a dead ringer. It's exactly equal to the population mean. So I could have just left that symbol alone, but I'm being consistent all over the place here. So since we're using X bar, we're adding X bars all over the place in this formula. So you can see the skeleton of the formula is still intact in this new extra crispy formula. I'm just adding X bars all over the place because we're using means instead of scores. The mean minus the population mean of means, divided by no longer just the standard deviation, not just sigma anymore, but now sigma X bar, which you learned in the last couple of episodes. In the last two presentations, I talked about this new thing, this standard error of the mean. Okay, sigma X bar is the standard error. So we divide this thing by the standard error, and that will give us a z-score. Now don't panic here also. I've given it the little subtext X bar. A z-score is a z-score. I'm just trying to be consistent by using the X bars all over the place. So don't get confused and think, oh, we got a new thing here. A z-score is a z-score, okay? You could just as easily leave that out. But I'm using, I keep it all in there so that you know that, oh, we're dealing with something different here. We're dealing with the sample mean now, not just an individual's score. Okay, so this is how we're going to take the sample mean and convert it to its respective z-score. And then we'll turn to the z-score table exactly as we've been doing. Likewise, we can turn this all around and we can ask and answer what I call backward problems. All right, that last set was what I call forward problems, where you go from a individual or a sample mean, work forward to get a z-score, and look in the z-score table to get the percent and percentiles. We can work backward if we already know the percentile and we want to know what score or now what sample mean is associated with that. We'll do what I call backward problems. Backward kind of problem here now in this new context would be something like, for a sample of 20 people, for an N of 20, what would be the mean needed for them to be in the 95th percentile? So see, I already know the percentile. I'm not working forward to figure out the percentile. I now need to work backward to figure out what the mean is associated with that. What mean would be the 95th percentile mean? What sample mean would you need to have for you to be able to say, hey, this sample is in the 95th percentile. These 20 people are in the 95th percentile. We went backward with the original formula doing that. So now we were solving for X, and we plugged in what we knew here, the population mean, the z-score, and the standard deviation. Well, likewise, in the last formula, we were, I added X bars all over the place. So now this is our formula, our extra crispy backward formula for figuring out what the sample mean is. To get that, we just plug in the population mean, which is the same as the mu X bar, the mean of means, is the same as the population mean. So plug in the population mean, the appropriate z-score, which we'll see in a moment, plug in the correct z-score. So you go to the z-score table in a way you'll see in just a moment, and plug in the z-score and multiply by the standard error. And then we use the z-score table exactly as we did before. Now the biggest difference in all of this, the extra step that I made reference to earlier, is that instead of using just the plain old sigma, the plain old population standard deviation, we need to use the standard error of the mean, right? We used this little doohickey, the sigma X bar, instead of just sigma. Now recall that we get the standard error from that beautiful formula that I gushed on upon in my last presentation, all right? This is our E equals MC squared in social research. This is our way to estimate what the standard error would be, because we would never, by God, go out and actually get it. We never will ever go out and get the actual standard error in the brute force method of going out and getting every single population, every sample that we could conceivably get from the population. No one's going to do that. But beautifully, we have this way of estimating it very precisely. We will use that. So you still need to know sigma, so instead of using it just all by itself, we plop it into this formula and divide by the square root of whatever sample size we're using. and estimate what the standard error would be. And just to go back, that's what we plugged in here. We'll plug it here in the backward formula, and back one more step, we'll plug it in here in the forward extra crispy formula. All right, so let's go back, forward. So as long as we know these four things, we're set to go here. Okay, we still need to know the population mean. We still need to know the population standard deviation. We, of course, need to know the mean from the sample that we're studying, and that's in our control. We know how many people we've studied, so we know n. So if we know the size of our sample and what their mean is, and these two population parameters, we're ready to go forward and backward. We have everything we need. So let's try it out. Let's try out this new extra crispy forward formula. Here's a typical kind of question that you have with an extra crispy forward formula problem. Say that we have sampled 9 students. I got 9 kids, and I found that their mean IQ score is 105. So collectively, those 9 kids have an IQ of 105. For the group of 9 is 105. Now, stop and pause. If you just randomly selected 9 people from the world at large, what would you sort of expect this mean to be equal to? The population mean IQ is 100, right? So already I can see, oh, this is a little, this group's a little bit above average, all right? If they're truly randomly sampled, I was expecting the mean to be approximately 100. Well, this is a good question now. So once we figure out what percentile this is, we'll know whether or not this is normal or unusual to get 9 people to have a 105. So that's the question. What percentile is this sample mean? What percentile is a sample mean of 105 when you got 9 people in a sample? I always say start with a picture, okay? Stats is confusing enough. We're all visual learners. Everybody is. So it's always gold to start with a picture. Let's draw a picture of what we got here. We have a sampling distribution now. This is not the raw score population picture anymore. This is not a frequency distribution of raw scores. It's a picture of my theoretical sampling distribution for an n of 9. All right, so this is how I imagine that if I were to go get all bazillion groups of 9 that I could conceivably get, calculate their means, and pile them all up at once, the central limit theorem says it ought to approach normal. Now, sample size of 9 is kind of on the small side, so we're in iffy territory if the central limit theorem is really going to do its work to produce that normal shape. But I'm fairly confident that it does, especially since we're starting out. This problem has to do with intelligence, which we do know is normally distributed already in the population. In the last presentation, I showed you that if you have a normal distribution to begin with, the central limit theorem is really good at producing a sampling distribution that's normally distributed, even with a sample size as low as 9. So I remain confident that this is a picture of this is just a stock picture. I don't know if it's really that tall and skinny, but I'm confident it's normal. I'm going to go forth with this confidence that it's normal. Now, my one sample of 9 people, I'm pretending I got one group of 9 from the bajillion samples I could get. So they're in here somewhere. They're piled up in here somewhere. Well, where exactly are they? The population mean IQ is 100, so the mean of means for all of these samples is also going to be 100. So that's what I know so far, that the bazillion samples are piled up under this curve. And 105 is up there somewhere. Let's draw it there. It doesn't have to be to scale. And so there's my question. My question is a percentile question. So in other words, I want to know what percent of this pile of means, what percentage of this pile of samples would be at or below this sample mean of 105. I'll say that one more time. What percentage of the bazillion means are at or below this one mean of 105? So there's a pretty picture of where we're going with this. And as I said, this doesn't necessarily have to be to scale. Let's just put a little reminder. I'm piling up what we know here. I know the population mean for IQ is 100. I know that the standard deviation of the raw scores is 15. I know that I have a sample size of 9 because I told you so. And I told you that those 9 people have a mean of 105. So the first step, as you saw, one of the side steps that we have to do is to go get the standard error of the mean. So let's go off to the side and do that. So plug in our formula here. And we know that the population standard deviation is 15, so I've plugged that in upstairs. I'm using a sample size of 9, so I put that under the square root symbol in the denominator. So 15 divided by the square root of 9, which is 3. 15 divided by 3 is 5. 5.00 to be Batman precise. So my standard error now for this hypothetical sampling distribution of all of the possible means that I could get is 5 units, 5 standard error units. Now let's plug this all into my new extra crispy forward formula. So there it is, my extra crispy formula. So my sample mean is 105. The mean of means is equal to 100 because up here, remember the population raw mu, the raw population mean was 100. Population mean is equal to the mean of means, so that too will be 100 over here. Okay, and I borrow my standard error of 5 that I just calculated and plug it in downstairs. So 105 minus 100 is 5. 5 divided by 5 is 1. Positive 1.00 to be very, very Batman precise. My z-score for this sample is 1. It's one z-score above the mean. The question again is what percentile. So now it's time to turn out, go to the z-score table. This z-score table is not the exact one that's in your textbook, but they're all the same. So I have 3 columns. The first column is the z-score, and so I go down and I find a z-score of 1.00. Column B tells me the area between the mean and the z-score. And if that's confusing why I'm looking there, let's come back. Let me pause here. Let's go back to my picture. Let me go back to one of those pictures that I drew. I am looking now. I've decided that I'm going to build these two pieces together. To get the percentage that's here underneath this line, below this line, I know is this bottom half. 50% is in the bottom half. So 50% plus what's ever in this wedge between 100 and 105. That's the piece I need. That's the piece that is always in column B in our z-score table, between the mean and whatever z-score I'm looking up. That's the B wedge piece that I need. So if I nail these two pieces together, the bottom 50% plus this column B chunk, I'll have my answer. That's my goal. That's again why I forgot to say, that's why I draw a picture. I always say start with a picture so that this picture will steer you to a way of solving this puzzle. It's a puzzle. It's a little construction job. I see it's like building a little puzzle. I got 3 pieces of this puzzle. I need these 2. So I'm going to nail them together. That's one of 2 ways I can do it, and I'm not going to talk about the other way. There's always 2 ways to solve these problems. I'm just going to keep it clear and go with one of them. So back to the table. That's why I was looking for the column B chunk for a z-score of 1, which is equal to, as I circled here, a proportion of 0.3413. Your z-score table and this z-score, most z-score tables report these things in p-values, proportions, all right? My question was in percentage and percentile, so I need to convert that to a percent. 0.3413 is convertible to 34.13%. Just move the decimal places over 2 notches, multiply it by 100 to get the percentage. Okay, so that little wedge that I was just pointing out on that graph earlier, that column B wedge that I need is 34.13%. 34.13% of the population samples, 34.13% of the samples are in that wedge. Now add it to the bottom 50%. 50 plus 34.13% is equal to 84.13%. Boom. That's my percentile. As sample of 9 people who have a mean IQ of 105, places those 9 people, it places that collective group into the 84.13 percentile. 84.13% of the sample means would be at or below this group of 9. If I go, there's many ways to say this. If I go out and randomly select another 9 people, I could say there's a 84.134% chance that they'll fall somewhere on that portion of the population. Let's try another one. Let's walk through one more example that's very similar. So let's say again that we're sampling 9 students. This time their mean IQ is 110. So instead of 105, let's pretend they got a 110. What percentile is that sample mean if 9 people have a 110? Let's start with a picture again. So there's my theoretical picture of all the bajillion samples I could get. Mine's in there somewhere. Where's mine? Mine's right there now. It's at 110. Doesn't have to be to scale. So my question is, what percentile is at or below 110? What percentage of those samples are sitting there below that line in the sand of 110? Remind ourselves what we need here. The population mu for IQ is, again, 100 with a standard deviation of 15. I got 9 in my sample, but this time they had an X bar of 110. I need to determine the standard error. The standard error is going to be the same because I have not changed the sample size. I'm still using n of 5, and that determined what to divide this by. So again, I'll be borrowing the same standard error that I had in the last problem. It has not changed. My standard error is 5. Let's plug all this into the Z-score formula. So X bar now is 110 instead of 105. The mean of means remains 100, and I have the same standard error of 5 from the previous problem as well. 110 minus 100 is 10. 10 divided by 5 is 2. This sample is 2 z-scores above the mean. All right, I have a z-score equal to plus 2. I'm not putting the z-score table up. I'm trusting that you can now go and find the z-score yourself. Dig out your z-score table. Look for a z-score of 2 this time. And the same logic, the same problem, I want this piece that's in column B so I can nail it to the bottom half. So I have 50% below my mean of 100, and now I need to know this column B piece. So I looked in column, I'm skipping a step here, I looked in column B and I saw a p-value of apparently 0.4772. I multiplied that by 100 to turn it into a percent. So it's 47.72. 47.72% of the samples are between 100 and 110. And 50% of the samples are below it. So add those two together, 50 plus that equals 97.72. So voila. That group of 9 people, if 9 people get an IQ of just 110, collectively as their mean, that places them in the 97.72 percentile, just about the 98th percentile. This is rare. Anything less than 5%, there's less than 5% above them, right? There's 2.28, not even 3%, okay? Less than 3% of the means are above their mean. By definition, they are rare. It would be rare to get 9 people to have an IQ score of, collectively, a mean of 110. One person having a 110 is good, nothing to write home about, nothing to throw a parade for, but get just 9 people, gather 9 people together who collectively, one way or another, have a mean of 110, and that's rare. That's rare. Now put this in an experimental context. Let's now imagine that these 9 people were part of an experiment. They're in the experimental group. I got 9 other schlubs in a control group that don't get some treatment, and these 9 people got some kind of treatment. Again, a Barney Rubble vitamin to see if it will increase intelligence. Now we would counter this finding, these 2 possibilities, and we'd have a decision to make. On the one hand, these 9 people have a mean of a percentile of 97.7. They're rare. Okay, it could happen by chance alone. Perhaps they're there because of just sheer good luck, bad luck, whatever you want to call it. They just could be there by chance. It's a possibility. It's rare, but it's a possibility. It's rare that you'll win the lottery, but it's possible. All right? Not very likely. It's exceedingly rare. You get the idea. Rare things do happen. They just don't happen to you. Okay. On the one hand, we have a group of 9 people that are demonstrating something that by itself is rare, But on the other hand, the only conceivable difference between them and a control group, which let's pretend the control group is still somewhere around 100, they got a treatment that didn't do anything. They got an inert, treatment, a sugar pill, all right, a placebo, and it did not boost their intelligence in any, let's just pretend that group is still sitting there right around 100, somewhere here in the middle. And our group is over here with 110. So it could have happened by chance, or it could have happened due to my treatment. And so this is where we stand with inferential statistics. We weigh these two possibilities and we say, well, what's the likelihood that it happened by chance? And we say, it's rare. And so if we did good research, if the control group is just like the experimental group in every way except this stupid treatment that we gave, the Barney Rubble vitamin versus a lack of a Barney Rubble vitamin, if everything else is exactly the same, I would be comfortable rejecting chance. I would reject chance as the likely reason for this outcome and stand with a little bit of evidence, not proof. I haven't proven that the vitamin is the reason for the increased intelligence. I just have evidence supporting it because the other alternative is chance. It's exceedingly rare. It's very unlikely to get this kind of a result, especially in comparison to another group that's sitting there performing like nothing happened. They're sitting there with their mean close to 100, and this group's at 110. That's inferential statistics. That's why we do this, and that's how this works. Getting 9 people up to a 110 is kind of wild. One person having a 110, no big deal. No, don't throw a parade for the person coming home with an IQ of 110. But maybe throw a parade for 9 people that come back with an IQ of 110. And again, a mean is just that. Doesn't mean every person got 110. Hey, it's conceivable that the vitamin only affected one person. Maybe one person had a really high IQ and dragged everybody else along with them. That's possible. That's why we look at the raw data. That's why we look at the data. Did most people go up? Was it an outlier? Stuff like that. So if there's nothing else funky about this group of 9, they just kind of seem to have gone up collectively, I start to wonder about the treatment I gave them, if I gave them a treatment. If I didn't give them a treatment, I wonder, what are the possible reasons? Maybe I just got a weird lucky group here. I grabbed 9 of Metcalf students in stats that are just really brilliant, all by themselves. They don't need pills. They're just smart people. Maybe that's what happened. So anyway, you still have to be a human being and assess what might be different about this sample. And if you know that, hey, this sample's just like another sample that I didn't give a treatment to, it gives you that much more probable evidence to suggest that it might be due to your treatment and not so much due to chance. That's the future. Let's stick with the present. Let's turn it around now. Let's try a backward problem. Let's try this out for the first time, my extra crispy backward formula. So we have a different kind of question, and I'm going to change everything here, okay? So let's say we raise the sample size to 36. Now I got a whole big class. I got 36 people. And the question I want to know is, what sample mean would I need from those 36 to put them into the 90th percentile? In other words, what mean do they need to have to be placed in the 90th percentile? Let's start that, of course, with a picture. So there's my picture of my theoretical pile of samples of now 36. No longer samples of 9. Now it's 36. Not 36 samples. There's a bazillion samples in there, all of a size of 36 people each. This is a picture of all of the unique samples of 36 I could get out of the population. Every single one of them. They're all there. If you put another one in there, it would just be a repeat of one that's already in there. I already got all of the unique combinations in there. They pile up that way, and I know it's an IQ problem, so I know that the middle of that sucker is going to be 100. Where would 90 percentile be? So I'm going to draw it kind of approximately. It doesn't have to be to scale. Right around there, okay? That's a line that I think cuts off 90% or at or below it, okay? Leaving just 10% above it. Only 10% of the means would sit above this number. So that's the question. What is that mean under there? What's the mean sitting there under that line? What does that 90th percentile mean? So using this information, we can determine that we need to determine the z-score needed for this percentile problem. So like I just said a moment ago, if there's 90% below this mean, then there must be 10% above it. I am going to need the z-score now. Now I don't get the z-score in the forward fashion. The forward fashion, I use a formula to calculate z. Now I'm going to consult the table and look for z. I'm going to go in with a percent and come out with my z-score instead of going in with a z-score and coming out of the table with a percent. Now I could use column B to figure out what z-score is there, because there's a B piece right here. And if this is 90%, I didn't label it all, but if this is 90% below it, and that's 50%, column B must be 40, right? So I could go in column B and look for a z-score closest to whatever would be for 40%. I'm lazy though, and I chose to go with C. I just blew my laziness by pointing out how to get B, but it took extra steps. Column C was easier. If that was 90, this must be 10, because the whole thing's got to add up to 100. So in column C, I know that, hey, 10% is associated with column C. Now the z-score table, again, is in proportions, p-values, not percent. So I have to convert 10% to a p-value. So the closest, 10% converts to a p-value of 0.1, right? 10 divided by 100, okay, to go backward to get a p. So a p-value of 0.100 is 10%. So now my task would be to go in column C and go rifling through column C and find a number closest to 0.1000. Sometimes when you do this, they're not in there exactly, okay? You might not find the exact p-value, and I believe this is one time when that happens, all right? So you find the nearest one, the closest value. I'm looking for the column that's closest. I'm looking for a z-score now closest to a 0.1 in column C. So if you dig out your table and do that right now, pause this and dig out a z-score table and look in column C for the value closest to 0.1, and then go over with your finger and look in the first column, and that's the z-score. That z-score that's closest, I looked up, it's 1.28. So the closest z-score is 1.28. I'm about halfway there. I'm halfway to solving this. I don't know what that magic mean is yet, but I do know it's a z-score of 1.28. Okay, I'm halfway there. If you don't know what I'm talking about, rewind this, review this, look in your book, dig out the z-score table and make sure you can see how I did this. I'm going to move on now though. Okay, I got a z-score of 1.28. And I'm going to need that backward formula. So up here I just have my usual reminders. I know I got a population mean of 100. I got a population standard deviation of 15. I got 36 in my sample. I'm looking for the 90th percentile. I found out that that's associated with a z of 1.28. 90th percentile is a z-score of 1.28. To use that backward formula, look at here, I have a standard error in it. So off to the side, I got to go calculate a new standard error. It's new because I'm using a different sample size now. I'm using 36 instead of 9. So 15 divided by now the square root of 36. 36 square root of 30. I'm using simple numbers here that I don't have to pull up my calculator for. The square root of 36 is 6. So 15 divided by 6 is, rounded to 2 decimal places, is equal to 2.5. So my standard error now is 2.5. So I slide that in, I'll borrow it and put it in, plug it in for my standard error portion of the equation. The z-score, which I just looked in the table for, again, was 1.28. This is where it's very important to know if it's on the positive side or the negative side. Okay, all of the z-scores in the bottom half of the table of the distribution are negatives. And so when you find one that's on the negative side, you got to plug in a negative, right? Because you're going to, that makes a big difference. I'm about to add this to 100. So if it was a negative, I'd have to add a negative, which would be subtracting. So it's a great big difference if you need to subtract. But this was on the positive side. Let's do this step by step. 1.28 times 2.5 is 3.2. Add that to the population mean of 100. So my mean is 103.2. There we go. The 90th percentile mean is a mean of 103.2. So the question again was, what is the mean needed to be at the 90th percentile? 103.2 is the mean that you need. All right, let's think about that for a second. All right, if you get 36 people now, okay, a good-sized class, all right, big class, 36 students in a class. If they wound up collectively having a mean of 103.2, that's getting up there. That's not rare yet. They're not, there's 10% above them. So our definition of rare is, they need to be up there so that 5% or less. Okay, but they're getting up there. 90% are at or below them. Just 103. I kind of doubt that if I was talking to one person, if I was talking to two people and one of them had an IQ of 100 and the other one had an IQ of about 103, I'm not too confident that I'd be able to tell the difference between them. I don't think there's that enormous of a difference between 103 and 100. They're a little bit smarter than the 100. So it's maybe a little surprising that if you get 36 people up there who bump up from the expected mean of 100 to just 103, they're getting up there, 90th percentile. Only 10% are above that. 90% are at or below that group. So that's kind of interesting. So there's one example for how to go backward. All right, so let's pause for a big grand review here of what we've covered in recent things here. We started back with variables that we were pretty sure or were certain are normally distributed. Things like IQ. We've done a lot of IQ problems, which we know is normally distributed. When something's normally distributed, we saw that we could standardize things by fitting that normal distribution to the problem and using z-scores in a z-score table. So convert everything to z-scores and you now have a standardized system, and whether it's IQ or shoe size or the size of people's thumbs or how many shirts they have in their closet or how many times a bus stops per day at a bus stop. I don't know, these things are probably fairly normally distributed. So they're all very enormously different kinds of variables. And once you plug them into this standardized system and convert things to z-scores, you got them on the same scale. That's what standardization is all about, putting things on the same scale. Literally figuratively comparing apples and oranges. All right, we learned how to convert any score to a z-score using my simple, what I now call the original recipe. This is the original forward recipe for taking a score, converting it to a z-score. We use that information in the formula to work forward to answer any kind of question about percentage or percentile. Then we flip things around and learn how to work backward from percentages to raw scores. So we could have asked a question like what individual score. A moment ago I was talking about what mean. Now I'm talking about a score. What individual score would be needed to put that person at the 90th percentile? And we would use that original backward formula, original backward recipe. Then we marched on and we learned about the concept of sampling distributions and the central limit theorem. So we turned a corner and we went from individuals to samples. Now we're working with samples like we do in real life research. We're not really concerned with individuals anymore. We're looking at groups of them, particularly with an eye towards doing experiments or big surveys. So big correlational studies or experiments where we're dealing with mounds of people instead of just one at a time. So we needed those two concepts, the concept of sampling distributions and the central limit theorem put together to give us this ability to continue to use this concept of a normal distribution. The central limit theorem says that if the sample size that we're working with is big enough, then the resulting theoretical sampling distribution will be normal. Aha, if it's normal, I get to keep using z-scores and keep using this stuff I know how to do. And the bigger you make the sample, the larger the n is, the even taller and skinnier this normal distribution will become. All right, so we love normal curves. So we learned all about them. We continue to use them. Okay, now in the process of doing that, we learned all about the standard error of the mean and this new wonderful way to estimate it. This beautiful little formula saves us and spares us from the failure of never being able to do research, because we would never be able to go out and get otherwise without it, we'd have to go get every single sample. Research would come to a screaming halt because nobody has time to do that. Nobody has the ability, so we would never get anything done. So thanks to this wonderful little formula, we get to proceed and do research. We put this all together in a new extra crispy formula, and we have a new extra crispy forward formula for the z to figure out percentile. And when we know the percentile, we can work backward to figure out the mean using this extra crispy backward formula. And I just walked through both of those. Okay, there we go. All of this required knowing the population mean and the population standard deviation, though. So it still has been a little bit artificial. Lots of times we don't know what the population mean and standard deviation is, so it's time to take one or more of those things away. But that's a lesson for another day. Whew, that was a lot. You might want to watch this one again, as painful as that might be. Check your book, read the relative portions of your textbook, and by all means hit me up if you have any questions. Thank you for your attention to this lengthy video. This was an important one, though. See you next time we take things away. Bye-bye.